Here's my the last picture of my a kind of dream. If there is some open system and low, then sometimes the entropy locally decreases. There some kind of life phenomenon appears. And this is an idea, so-called reciprocative structure by Ilya Prigozhin. And I want to understand the nature of all prime numbers, the set of prime numbers, in this kind of flavor, from a viewpoint of analogy between knots and prime numbers. But one of the most important analogy between knots and prime numbers is Piazza theory. Alexander Fox theory. And one of my main topic I have worked on is its p-adic design. And it has been mostly for the self-interest, but recently we've got some application to topology. Topology. That is profinite compression, rigidity theory. Sorry. And today's topic is mostly in this region. I'm not much familiar with gauge theory, but Alexander Fox theory is U1 gauge theory, as Ozansky pointed out. So I think it's not so strange to give a talk about this topic in this conference. But after Park's very important talk, my talk will be something like a snack for morning coffee. Here is a plan of this talk. I'd like to recall some classical numbers. K is a finite extension on Q. Then the plus number is one of the most important. Last group is an important object. It is a finite group. Finding a number field with a trivial class group has been of great interest from Gauss. He studied a quadratic extension and asked if there is infinitely many such fields with a trivial class number often. Weber studied the cyclotomic ZP, cyclotomic extension. And it is conjectured that all P and N, but it is proved only for very limited cases. along this context, your source theory. Your source theorem is an important one. Let this be a system of cyclic p-path extensions. Then there exists that p torsion, size of p torsion is given in this way. It is extended by Pogmonsky. For system of product extension, is a similar form.
What is this? Sorry, what is the conjecture on the class number for cyclotomic fields?
The size is 1 for any p and n.
Number can't be 1, right? I mean,
If it were 1, the Fermat problem would have been solved much earlier.
Maybe something's wrong in this blackboard.
maybe the plus part of the p p class numbers.
Yes. This should be.
I think this is totally real one, right? This is part of cyclotomic ZP extension over Q.
So the k e to the n is
I think
okay, that's the.
I think K P to the N means the layer of the cyclotomic.
Okay, yeah, so that is the plus part. You're right.
Today's focus is slightly different. This is due to initially announced by Synod and written by Han. And afterwards, it was written by Kizilevsky. Afterwards, Yosaki also found and extended by is. And the class number converges in ZP. Since this problem is very difficult, it is almost impossible to calculate the value. But maybe we can explore some nature. In the Knox theory side or in the elliptic curve side, we have explicit formula for the size of these loops. So we can give more explicit numerical size. That is the main focus of today's talk. Number these accents. In two-dimensional topologies, XP compact three-dimensional topology is surjective homomorphism to ZP or ZP. Then we obtain a sequence of the compatible system over Z over P and Z covers. In this situation, we have an analog co-common scheme. Or the torsion size of the torsion subgroups. When d equal 1, we have an analog of synaptic skill type theory. Is the size of torsion subgroups converge in ZP. After we proved this theorem, we noticed that Gion case p-adic torsion is this. So we are also giving an example for Gion case. In order to make a numerical study, we have box Weber's formula. This Weber is different from number theory and more recent. And for simplicity, we just consider not in S3. Okay, we are not in S3. Let this then not be Alexander polynomial. Then we have a sequence of Z over NG above. And it's the size of this group is given by the cyclic resultant. And this is the product of the value at roots of unity. In order to state our theorem, we need to fix an embedding of an algebraic closure of rational numbers to the completion of the algebraic closure of QP. The following lemma plays an important role. Let alpha be a number on the unit circle. Then there exists a unique root of unity. Whose order is prime to P. And it's in the neighborhood of now we state our theorem for polynomial. Let f be a polynomial. For simplicity, we assume that p does not divide. N to be the cyclic lemma. And by this lemma, we have noting that this value is on the unit circle. And for each alpha I on the unit circle, we also take resolvability. Then, by using this, we can strictly write the limit value. And if this limit value is equal to 0, then we also have the formula for non-p part of this part. Here, the mu is your source mu invariant, and this log is the p-adic logarithm. It seems not. This seems a bit complicated, but you can say as a corollary that if the polynomial is equivalent to a cyclotomic polynomial modulo p, then we can say that the limit value is the value of this polynomial at equal 1. So the situation is mostly presented by the cyclotomic polynomial cases. I'd like to exhibit some intuitive concrete examples. The twist knot where n is any integer is defined by it's Alexander polynomial is this. J2 minus 2 is the for one, figure 8 node. That's right. Then the limit value we have and can verify that yes. We can also prove that after this part, every limit value does not belong to Z. I showed the calculation of this value. If p equals 7, then the eighth cyclotomic polynomial decomposes. And the Alexander polynomial is equivalent to this polynomial. And this calculates the limit value. Indeed, we have a complete list of the cases. Cases of I mean M and P. This limit value belongs to. In Pionke's paper, this condition is set called Atiyah's conjecture. I don't explain much about this. Another direction is to change the base space. We consider this sequence of covers, and then this polynomial plays a role. And we may prove this form. Maybe this value is transcendent. In general, we have for this type of sequence of covers. For which mu can be large, while the base space is small. I just show one example. This is kind of just for fun. If we consider this node and this sequence for covers, then this value is small, but mu is in this case mu is 100. To make this story more interesting, I'd like to look at the elliptic curve case in 2 or 3 minutes. Let E be an elliptic curve over Q, and suppose that it has good reduction at P. Then consider the a constant extension. N. Then the Frobenius polynomial plays a role. And this is so-called Frobenius trace. And the class number is given by cyclic resultant. We can verify that following table. The limit value is 0, 1, 2, if and only if P is 1, 0, minus 1. And in this case, P is called anomalous or super singular. Not anomalous. We have no name for these cases. And last December, we gave a talk at Kyoto University, and many number theorists asked us that about an analog of Lang-Trotter conjecture or LP's theorem. But things there is some constant, and this function is approximated by this function. So this set is an infinite set. The density is 0 in the set of all prime numbers. And one asked about an analog of this situation. I haven't yet go much in this direction, but there is a candidate. Is so-called modular number. For instance. And if asked me, then I can explain a bit more, but maybe I should stop here. Thank you.